One topic which often comes up is the prospect of asteroid mining. This then brings up the essential subjects of which asteroids can be mined, could it be economically viable, and what are difficulties involved both in mining the asteroid and in returning any associated assets back to Earth, along with the associated economic impact of actually bringing those assets back. Firstly, there are several different types or categories of asteroid that we know of. Most common are the Klondike asteroids, which are the rocky bodies mainly made from silicates and clay-like materials. This makes these asteroids dark, meaning they don't reflect much of the light of the sun, in turn makes them more difficult to observe unless they come fairly close to the Earth. Then there are the stony asteroids, which are nickel and iron asteroids combined with a substantial amount of rock, with the inner core of the asteroid likely to be mostly metal, with the rock forming the outer crust of the asteroid. And finally, there are the metallic asteroids, which like the stony asteroids contain nickel and iron, but without the stony outer shell. And it's these metallic asteroids which are the focus of some of the missions to the asteroid belt, like NASA's mission to 16 Psyche, and these metallic asteroids also represent a potential target of asteroid miners. The hope one day is to mine these metallic asteroids to the metals they contain and bring those metals back to Earth. These metals may also include copper combined with nickel in the form of Monel, as well as smaller proportion of gold and other heavier metals. Due to these asteroids not being covered by large amounts of rock or clay material, metallic asteroids tend to have a fairly shiny and reflective surface, making them easier to observe when light from the sun strikes the surface. This also makes the metals easier to mine than on a stony asteroid, where the mining of the asteroid would be many times more difficult than mining on Earth just for a similar game of materials. Now, the asteroid 16 Psyche is a metallic asteroid over 250 kilometers across, which if it wasn't in the asteroid belt would put it in the same category as a very minor planet or maybe a larger moon. While we know the approximate size and mass of the asteroid, we don't know the specific chemical composition of the asteroid or even how it was formed. It's this lack of information is the key reason why NASA is sending a mission to visit the asteroid, and also why others with more mercenary motives may be closely studying the results. Now it's possible that 16 Psyche was a protoplanet which failed to gather enough mass to actually become a planet, so it's basically a planetary core orbiting in space. Alternatively, 16 Psyche may be the remnant of some planetary collision with a solid metallic structure of the asteroid being difficult to fracture into smaller pieces. So 16 Psyche has remained as one massive lump. A lump actually might be the correct description for 16 Psyche, as the body is too small for the gravity created by the mass of 16 Psyche to form in the sphere-like structure of the major planets. So 16 Psyche is a fairly irregular shape known as a Jacobi ellipsoid, somewhat rounded stone you might find washed up on the ocean shoreline. This irregular shape does mean that once NASA mission gets close to the asteroid, orbiting is going to be really tricky. So the approach is going to be cautious and slow, take as many readings from orbit as possible. And the Psyche orbiter is equipped with many devices to scan the asteroid as possible. And we'll start scanning once it's within 700 kilometers of the surface, with the final scans taking place from an altitude of 70 kilometers. That's of course if the orbiter survives the closer approach. Now these scans will include a multispectral imager with 8 filters to basically map out the surface of the asteroid, give visual clues about the surface conditions, and even map the specific shape of the asteroid, which could be vital for any future landing on the asteroid. In addition, there's a gamma ray and a neutron spectrometer, which can hopefully tell NASA what the elementary composition of 16 Psyche actually is, along with the dual fluxgate magnetometer, which investigate any evidence of remnant magnetization. And similar pieces of equipment to this have been flown over the Earth's oceans and be able to scan the seafloor and feed back useful information as a result. Now, the orbiting part of the mission is designed to take 20 months, with the results probably taking many years to fully analyze. The Psyche orbiter was launched in October 2023, will take until 2029 to actually arrive at 16 Psyche. At the end of the mission, NASA hopes to show what the chemical composition of the asteroid is, how those chemicals are distributed around 16 Psyche. So answering the question, does the asteroid have a dense metal core like a rocky planet? If it does have a metal core, did that core at one time generate a magnetic field, indicating that the core was at one stage both molten and also creating the dynamo effect? Alternatively, are there metallic crystals distributed in concentration lumps around the asteroid? The other question I hope to answer is how 16 Psyche cooled, which again could give insight into how it originally formed. So once all this information is available, will there be a queue of billionaire asteroid miners buying up spacecraft targeting 16 Psyche to extract the mineral wealth contained within? Well, probably not. So why, if the potential value of the minerals in asteroids have been thrown around as being in the billions or even trillions of dollars, won't somebody try to exploit the resources? Well, starting with practicalities, NASA's Psyche orbiter is going to take 6 years to get to 16 Psyche. So the timescale for any potential return on a massive investment in asteroid mining venture is going to be a very, very long one. Next, NASA is only orbiting 16 Psyche, which is risky enough, but landing on an asteroid is going to be extremely risky, and as due to the time delay in communication with 16 Psyche, any landing will have to be entirely automated. Then, if a landing has been successful, you also have to hope that your mining equipment has landed undamaged and can successfully extract enough wealth from the asteroid to make the journey worth it. Currently, we have the technology to extract samples from planets, moons and asteroids. We don't have the ability to mine in quantities required for commercial mining. It isn't just a heavy equipment that will need to be transported, but also a means of powering that equipment, which will create difficulties. And whilst there have been some huge valuations for the mineral wealth of an asteroid, this is for the whole mass of the asteroid, not what a single mining operation might be able to extract. Not only might the operation not be able to mine only a fraction of the asteroid, might also not be able to reach the more valuable metals which potentially could remain out of reach in the core of the asteroid. Even then, once you've mined your resources, you have the tricky issue of getting them back to Earth, another journey which will take years to complete. The awkward manoeuvring and deorbiting the presumably heavy ore-laden craft safely back to Earth. Now, ditching in the ocean would be rather defeating the object of the exercise, and landing in a populated area would be considered unreasonable. So it's going to have some difficulties there. And once you have the minerals, you need to sell them in an attempt to recover not only your costs, but also maybe make a profit. Here we come across the economic issue of the valuations put on asteroids and the resources they contain. Currently, these resources have a value in relation to both the demand for the resources and the limited supply. Now, a sudden new supply of a particular metal is likely to depress the market for the price of the metal, not only reducing any returns for the asteroid mining venture, but also potentially creating a damaging economic impact, destabilizing the market in those resources. It may again make asteroid mining project deeply unpopular. However, it isn't all doom and gloom for future potentials of asteroid mining. Some of the costs involved could be reduced rather than delivering a single one-off supply from the asteroid. Once an automated mining operation has been established, a shuttle service could run from Earth to the asteroid and back, making a regular delivery once the mine has enough supplies to make the journey worthwhile. In addition, economic issues might be offset by depletion of the Earth's resources. Minerals being delivered have become rare or hard to obtain on Earth. Supply for an asteroid may not be massively impacting the value of the goods being transported. A final saviour for the concept of asteroid mining might be that the resources don't actually need to be returned back to Earth at all. Resources from asteroid mining could be returned to orbit, enabling construction of space stations and satellites around the Earth, without the need for launching required parts from Earth. It would save on costs and minimise the economic impact on Earth. Alternatively, resources could be used to deliver to a settlement on Mars or the Moon, enabling a permanent off-world settlement to actually be established there. So there are possibilities for asteroid mining.